Because for all these main patterns, roughly only need less than 5 default processes instead. Because there's not that many patterns inside, like etching.
You mean the number of litho steps
Yeah.
in total?
Yeah, it looks like it doesn't need that many.
Doesn't need many, yeah. Yes, doesn't need many. Of course, this we only show the key steps here, but the litho step is not that many. Yeah, that's a key concept, right? We need to reduce the number of litho steps to reduce the fabrication cost. That's why when you get more layers, then your cost per bit will reduce. That's how you get higher density, lower cost. That's a key concept.
And also, how do they make the contact, the last step, second of line contact with each step?
You mean the staircase?
Yeah, like on the staircase, they also have some metal contact on it.
Yes.
So how it looks like standalone metal directly on connected with these staircase.
Through the weir, through contact weir. Yes. Yes.
You have to etch each via separately though because it's on a different level.
No. You can selectively etch, right? Yeah. First you make the staircase and then you, it's okay, right? If you have selectivity, it's okay.
Yeah.
Oh, so this metal is already made out there. It just after it etch, it will show the metal contact.
Yeah, I think so. Of course, I don't know the details, but I don't. There's just one litho step there. Yeah, you don't have the different litho step for different layers contact. Okay, so those are the technology of fabrication issues, and then let's move on to the chip circuit result. So this is the first paper by Samsung, and I think that year Samsung also commercialized this 3D NAND into the market, and then the chip details disclosed in ISCC 2014, and this is 128 gigabit chip, and it has 2 big planes, and it has 24 layers in the first generation, 24 word line layers, and then this is the overall chip. You know, this is the memory cell, and then this is the peripheral circuits. So array efficiency you can easily tell. So then this is what I want to show. Okay, if you want to see, this is a TEM under the reverse engineering. And this company called ChipWorks is well known for this kind of reverse engineering. And so basically, they cut the sample and then take the TEM image. And here is the this is a cross-section view, and here this is the memory cell array with those pillars, and here is the whole staircase. You see that? And then there are many contact there, 2 different layers. And then this is a zoom in for this part. So you see the vertical channel.
That is very nice.
Yeah, this is amazing. This is even first generation, 24 layers. Today you will have 128 layers, you can imagine. Okay. So I don't have the updated, reverse engineering results. So this is amazing. You look at how well etched. And then this is from the top view. From the top view, and look at each of the hole. And then if you zoom in, each of the hole, you will see the stack. That's the silicon nitride as the charge trap layer. And then the array architecture is organized like this. Okay, it's 24 layers in terms of the word line, and then still we have the top string select, and then here in this case they have 8 string select, top string select as one block. And let's say 8 strings here share the 0 to 7 share this bit NAND, and this is one block. Of course, this side, this is only 8. This side is very large. This side is 8 kilobytes, and you know it's a 16K bit. So this is the dimension of this array. This side is very long. You have like 16K bit NANDs per block. And then this string along this dimension is 8 string share this one bit NAND. And then vertically you have 24 layers. Okay. So this is one block. Of course you have many blocks in this 128 gigabit chip. And then in terms of the cell characteristics, it shows better result than the 2D NAND in terms of the, for example, the vibration. So here is the, let's say the threshold distribution. So you see the 3D NAND shows tighter distribution, okay, than the 1x nanometer 2D NAND. And also the coupling becomes better. So as we discussed, the key challenge for the 2D NAND is the cell-to-cell coupling. That is here, showing here is 1x nanometer, right? So this initial VTH is this distribution, and then you program the adjacent VLAN, then the distribution shift to be this guy. Then this is not good. But for the 3D NAND, you see the before the adjacent VLAN programming, before and after, you see here those two almost overlap. That means no shift in the VTH. This is good. So then my question is, why would the 3D NAND become better? Any idea? Any idea? Actually, some of you asked this question earlier. What is the diameter for that vertical channel? I said it's large, like maybe 100 nanometer. So the 3D NAND, the feature size actually is relaxed compared to the 2D NAND. For example, the diameter, this is maybe 50 nanometer. And the height of each cell is also relaxed. So think about this 3D NAND. Let's say this is one layer. So first, this one is, of course, the first generation maybe 100 nanometer, but in this days typically let's say 58 nanometer. And each cell, similarly, if you look at this, will be a little bit less than the, let's say, half of the diameter. But in this is first generation, let's say. The height, let's say 60 nanometer, let's say 30 nanometer, maybe. Each layer from the source to drain of that vertical transistor. So the dimension is much relaxed. So this will help, right?
But then in three-dimensionally, you have more other cells surrounded in 3D and 2D.
Not really. You will have some in those, let's say, those diagonal directions, right?
Yeah.
But the distance is far away. Look at those nanometer. In 1x nanometer, the distance around, I mean, between adjacent cells maybe like 20 nanometer or less. This guy is like 50, 60 nanometer, right? So the distance will matter. So here the key is that those dimensions are relaxed. So the coupling is less, and also the cell area, let's say the gate area, will be larger. So you can have more electrons into the gate. So variation will be smaller, and retention will be better. So the reason here is that you don't need that density from the two-dimensional scaling. The 2D feature size is larger, but you have more layers. So the density is still higher in this case. So any questions here? And then from the chip level, the performance gets improved. So here is a comparison between the 2D NAND, 1x nanometer 2D NAND, published in ISCC 12 from the Samsung, and with them own work, the first generation ISCC 14, 24 layers, 3D NAND. So the memory capacity doubles from 64 giga to 128 giga. And then the performance, internal, like the write bandwidth, increase from 33 megabytes per second to 50 megabytes per second. And the key result is this one, the density, because we care about the density, right, for the memory business. So the 2D NAND is 0.58 gigabit per millimeter square. And then this become like 0.96 gigabit per millimeter square. So just increase by 1.6 times, okay? It's not 24 times. You don't think that 2D NAND is one layer, this 3D NAND is 24 layer. So the density increased by 24 times. But actually only increased by 1.6 times. Why is that? Any idea? We discussed already.
Yeah.
So we just said that the feature size relaxed quite a lot. This 1x nanometer, maybe 18 nanometer. That one maybe 100 nanometer, right? And the second reason is that you notice that the staircase, that area underneath that staircase is wasted, right? So in 2D NAND you don't have that wasted area in the peripheral. So in the 3D NAND, then underneath the staircase, those area is wasted. So this is, but again, you improve this by some factor, which is good. And from the system level, when you plug in as SSD, and then here shows some system level benchmark, and the performance become better, and power become lower, so everything becomes better. The density, performance, power, all of them become better. So this is summary of the first generation 3D NAND back in 2014. So I will not repeat the details here. So since 2014, and after that, every year, Samsung published one ISCC paper on the update of the 3D NAND. And this is 2015, and this is 32 layers, increased from 24 to 32. And the capacity is still 128 gigabits. But this one also introduces multi-level cell, in this case 3 bit per cell, so the density is really high. And if you compare the density, here it reaches about close to 2 gigabit per millimeter square. That is higher than the hard disk drive at that time. So it first demonstrates that SSD may have higher density than the hard disk drive. So this is the 2015. And 2016, again, this is improved. So I think the number of layers changed from 32 to 48. And the capacity doubles from 128 giga to 256 giga. So the density reach 2.6 gigabit per millimeter square. This is the third generation. And 17, this is fourth generation. And this compares 17, the fourth generation. Now the capacity increased to 512 gigabit per chip. And the density increased to close to 4 gigabit per millimeter square. So you see the progresses here. And it becomes 64 layers. So this is the fourth generation. And I think till 17, from let's say 14 to 17, Samsung is the only company that commercializes this 3D NAND. The other companies like Micron or SanDisk, Toshiba, Hynix, they start producing the 3D NAND, I think around this time, from 17. So they are like 3 years behind Samsung. But they are catching up quickly after that. For example, here, I think Toshiba announced some like 96 layers, like in 17 or 18. So they are catching up. All the other companies nowadays can do like 96 or 128. Okay.
So if you have 64 layers,
Mm-hmm.
then you have to read all the cells because they're all in the NAND. There's no middle connection. They're all in the same NAND
Yeah.
branch.
Yes.
Or 65. Okay.
No. I mean, if you look at the operation, it's the same as we discussed before. Okay. Right. So do I have that here? If you look at this 3D NAND structure, each string is like the 2D NAND.
Yeah.
The bias condition, I mean, this operation principle is similar. So when you read out this one cell, you are going to apply this V-pass read for other cells to turn on the other cells, and then you read one cell out here, right?
Yeah, but there's
For the programming, you need to inhibit other bit lines, the same thing. That's not, because from the circuit schematic point of view, it's very similar.
But there's still only 8 cells in one branch then?
No, in 2D NAND we have 64, right? Typically.
But the eight cells in a string are always read and programmed together?
No, so here, if you look at here, right, I would say you should, let's say, look at this plan. And if we look at, and if we label X, Y, Z, X, Y, Z. If you only look at the first plane here, the XZ plane, this XZ, we want to keep this. This XZ plane is exactly the same as the 2D NAND, right? From the circuit schematic point of view. So different XZ plane is selected by that SSL here, the top string select, right? So through this signal, you can select which XZ plane, and then after that, the operation returns to like 2D NAND operation, right? If you look at the first XZ plane, it's the same as the 2D NAND. So you just need to turn on this guy, and then turn off the other SSL. Okay, so here we just talk about this actually. We need to notice that the 2D NAND, the feature size is smaller. For example, if it's 15 nanometer. 3D NAND, for example, the feature size is 60 nanometer, the diameter of that pinner. So you just look at this ratio, you need at least 16 layers to achieve the same density. Because this ratio is 4 and the f square is 16. And then consider the area waste in the staircase underneath that word line contact area. So you need at least 32 layers for the 3D NAND to be better in terms of the density. So today, that's why the industry is pushing really hard to make this number of layers even higher. Of course, the challenge will be, as you pointed out, if it becomes 128 layers, then the RC delay along that pinner is very large. Okay, the current is so small to read out. Okay, this is a summary of the whole NAND section. So we talk about NAND, and this is dominating the market. And 2D NAND scaling is approaching the limit. So that's why we switch to the 3D NAND. And then we talk about the MLC operation, and also talk about the reliability degradations. And the 3D NAND right now is actually dominating the market now. And it will continue the stacking of the layers. I just read the news, I think last month, Intel announced 148 layers 3D NAND with 4 bits per cell. So you can imagine the density there. 148 layers, and each cell is 4 bits per cell. So these days you can get 1 terabit per chip. Okay, so any other questions?
4 bits per cell, 16 layers. 16
Levels, yes.
Wow.
So the density is very high. Alright, so that's the end of the